Okay, can you hear us now?
Yeah, now it should be working.
Oh.
Awesome.
Yeah.
Okay. Yeah, can you back to right before the problem?
Right.
Yeah. Okay. Yeah. Okay. So so I could use complex equivariant K theory. I would get an answer in the representation ring. What this tells me when I set up any problem, sort of in the setup above, I get a solution to it that is conserved. So an example of this, if I take the 27 lines on any symmetric cubic surface, and I let S4 act on these lines, and I look at that as a representation, that data is conserved. That doesn't depend on the choices that we might have made along the way. Okay. So the problem with this, before we had our technical issues, is I've got this map from the Burnside ring. Right? This is finite G sets basically. To the representation ring, and it takes a finite G set G mod H, and it just takes a copy of C for every left coset and lets G act on them. And that way I've got this permutation representation. And this map sort of fails very miserably to be an isomorphism. It will be injective in the case where I have a cyclic group. That's when it will be an isomorphism. And it will be surjective if I have a symmetric group, which is great for the purposes of our problem. But in general, it won't be surjective. Okay. So taking the representation that I had and trying to pull it back to something in the Burnside ring doesn't actually work. But we can actually, I can still use this in some cases. Okay, so why am I able to use this? Let's use the case of G equals S4. And this, symmetric lines on a symmetric cubic surface problem. What I have is I've got this A of S4 mapping to R of S4. This thing is 11-dimensional. It's indexed on the conjugacy classes of subgroups. This is 5-dimensional because it's conjugacy classes of elements. So, and it will be surjective actually in this case. But the problem, right, is that I've got something well-defined here. I want to pull it back to something here. I've got a Z6 worth of choices. But I don't actually want any element in the Burnside ring, right? I want something that's actually an S4 set, right? I want something in the upper orthant. This is a free abelian group on 11 things, and I want something where all the coefficients are non-negative. So what I'm asking for is I'm asking for solutions to an integral matrix where the entries in the solution satisfy inequalities. And this is the sort of type of thing that polyhedral methods in something like SAGE can take care of. Okay, so this actually, for the purposes of 27 lines on a symmetric cubic surface, this Euler class is good enough. And we can state a statement that says the 27 lines on any smooth symmetric cubic have the following orbits. Let me write these. I'm going to have a copy of S4 mod C2. I'm going to have another copy of S4 mod C2, but this is going to be a different copy of C2. There's two non-conjugate copies of C2 in S4. I've got the one generated by one transposition and the one generated by two disjoint transpositions, the product of two disjoint transpositions. And then I've got an S4 mod D8. Okay, and so this is 12 lines here. This is another 12 lines. And this is 3 lines. All right, so let me pull up a visual for this. So this is up on my website, but this is what these look like, the orbits on the Klepsch. We see our 3 lines sort of on the bottom, or what I think of as the bottom of the cubic surface, and then I've got these 2 groups of 12 as I rotate around. And this, like I said, won't depend on the choice of symmetric cubic surface. Okay. But I had still mentioned this problem, and it rears its head when you start to ask a really natural follow-up question, which is what happens if I look at subgroups of S4 and I look at these actions? Let's say I don't want the full S4 action. Let's say maybe I want a C4 action or something like that. Can I still make this claim, and can I still use these polyhedral methods to do this? And the answer basically is that, right, this is another problem. the KUG valued Euler class is insufficient. Maybe like for all subgroups of S4 on the cubic surfaces question. And it's insufficient if I want to make a broader theory of equivariant enumerative geometry. It's just it simply won't work. In 3 of the 11 subgroups of S4, you see that these polyhedron methods don't give you a well-defined solution. You know, I've got multiple non-isomorphic S4 sets where their permutation representations are isomorphic, and this is sort of a dead end here. So in the remaining time, let me just sort of say a really cool argument, which is attempt number 3. And this is to use something very mysterious, which is MUG. And this is complex homotopical Bordism. This is very different from geometric Bordism in the equivariant setting. So this was developed by Tom Dieck and Christian Okonek and a lot of people. It's a very, very mysterious theory. There's a lot of open conjectures about this. A lot of sort of recently resolved conjectures as well, but it's something that we don't understand well at all. But I want to sort of give you the following proposition, which is even though I don't understand pi naught of MUG, it still receives a unit map from the sphere. So the proposition that the unit map SG to MUG induces an injection on pi naught. Okay, so let me give you a sketch of the proof for this. And maybe sort of why do I, well, I'll say this afterwards actually. Okay, so the proof sketch is that what I would actually like to show, I want to show something slightly more general, which is the kernel of pi star G of the sphere spectrum mapping to pi star G of MUG is nilpotent. Okay, so why would this prove what we want to prove? When I restrict my attention to pi naught of the equivariant sphere spectrum is the Burnside ring. And that's a reduced ring. So if I see elements that are nilpotent in the kernel, they just have to be 0, and I get an injection. Okay. So I want to check that I have this sort of equivariant analog of classical nilpotence. And one thing I noticed is that I'm allowed to check this on homotopy fixed points. The reason for this is that the condition of being nilpotent is like a telescope condition, right? And geometric fixed points commutes with filtered colimits, so I can pass to geometric fixed points. This appears in a paper of Bardell, Greenlees, and Hausman. And then I use a computation of Deb-Sinha, which says that the geometric fixed points of equivariant MUG, so if I look at maybe like phi h of MUG, this is a wedge sum of classical MUs. And then I use Devenatz Hopkins Smith, which is this classical nilpotence theorem to conclude. Okay, so what does this buy me? This says that I've actually got an injection of A of G into pi naught of MUG. But it's more than just an injection. It's an injection that's occurring from a map on pi naught of ring spectra. In other words, it's really coming from a map of Timbara functors. So what this tells me is I've got these elements, you know, 1 being sent to 1, and I've got transfers that are sent to transfers. And so when I double back to this equation up above, let me copy this. If I look at this equation right here, if this is in pi naught G MUG, the statement that I want to say is this admits a unique preimage in the Burnside ring A of G. In other words, there is a unique G set whose Euler class has this value. And if I just count my solutions with orbits and I look at what that is mapped to in the Euler class, it has to be this sort of thing here. So this gives you a theorem that I might call, I don't want to get too like intense about this because there's still a lot of hypotheses that we want to lift on this sort of thing. But in the setup above, the G orbits of the solutions to our equivariant enumerative problem are conserved. Okay, so it's really like a go-ahead green light type of theorem for studying enumerative geometry in the presence of symmetry. This says that you should expect to see this type of conservation behavior that we'd like. Okay, so I'm almost out of time, so let me end with one last cool result that you can see out of this picture. And I said the Schläfli theorem earlier. And this is this theorem from 1858 that said there are 3, 7, 15, or 27 lines on a smooth real cubic surface. And the idea is we can actually refine this in the presence of symmetry. We can remove some of these possibilities. So on a smooth real symmetric cubic surface, so how many lines could I see? If I go back to my computation, I had these 3 orbits of lines here. Let me just copy this down to where we were before. Okay. So one thing I see is that if I take an equation for a line on a cubic surface, I either had to use imaginary numbers to define the line for you, or I didn't, right? And when I go and I permute the variables in the equation for the line, that fact isn't changing at all. I either needed complex numbers or I didn't need complex numbers. What that statement is telling you is that within each of these orbits, there is a field of definition to the line, and that doesn't change when I act by S4. In other words, all 12 of these lines are defined over the reals, or they're defined over the complex numbers. And when I look at that, I say, okay, well, I could either have 3, 12, and 12. I see immediately I couldn't possibly get 7. That's just not a possibility for symmetric cubic surfaces. And something even more is true. I had this distinction of real lines that I had hyperbolic ones and elliptic lines. It turns out that that statement is also conserved. So maybe all 12 of these are hyperbolic, all 12 are elliptic, something like that. And when I look at that possibility as well, I can actually rule out the possibility of 15 cubic surfaces. So the theorem is that on a smooth real symmetric cubic surface, there are either 3 or 27 lines. And an important part of Schläfli's thing was not just this restriction, it was actually the existence of cubic surfaces with each of these numbers of lines. And we also have existence for symmetric cubic surfaces with these lines. So this, an example is, for 3 lines, I have the Fermat cubic that has 3 real lines and it's symmetric. And the 27, I have the Klutch cubic surface, which is all 27 defined over the reals. Okay, I will wrap up there. Thank you so much.
Any questions?
Can you say again why you can rule out the 2 families of 12 lines?
Yeah. So this was, so I look at the fields of definition of these, right? And I say, okay, well, I can rule out 7 for sure, because I just can't combine 3, 12, and 12 to get 7. We're saying like a priori, I could have 15, right? I could have 2 of these defined over R and 1 defined over C. But then I look at this and I say, okay, well, either all 12 of these would be hyperbolic and all 3 would be elliptic. That doesn't quite work, because when I took hyperbolic minus elliptic, I should always get 3, and 12 minus 3 will be 9. Yeah.
Got it. Cool.
Other questions?
Could I ask? I'm wondering if there's a stronger group theoretic connection that I might understand. So the monodromy group of this configuration of 27 lines on cubic surface is the Val group
Yeah.
E6, I think. And
Yeah.
and so you've got S4 acting.
Yeah.
And that E6 acts transitively. And I'm wondering, is what you're doing taking realizing S4 as a subgroup of the symmetric group of S4, so subgroup of the Val group E6, and then seeing how those orbits decompose, which is a question of double cosets between that S4 and the stabilizer of one of the lines in E6.
Yeah.
But is that the same calculation? So it becomes a group theoretic calculation of double cosets, if you will.
Yeah, this is a tremendous question. And this is something I've been thinking about very recently. So anytime I have some symmetry on a cubic surface, if I think about, I'll just sketch this real quick. If I have my M33 and I'll take a moduli space with maybe 6 skew lines to generate all 27, I've got this WE6 cover that you're referring to. And basically, if I have a cubic surface with some group action, something like an S4, just by like definition of pullbacks in the world of stacks, like the S4 action will factor through the étal pi1 of the moduli space downstairs. And what this tells me is that the action on fibers is occurring as a subgroup of the monodromy. So that S4 is indeed living in WE6. In terms of what it is, I don't actually know. I ran some Magma code earlier this week, and it looks like there's 10 non-conjugate copies of S4 sitting in WE6. I'm not precisely sure which one this is.
You don't know? Yeah.
Yeah, this is something I would like to work out. But I think a related interesting question and something I've been thinking about very recently is if I restrict my monodromy downstairs to the locus of symmetric cubics, am I just getting S4 instead of the full WE6? Like if I take a loop downstairs, is that what I'm seeing? So this is something that I'm currently working on.
Okay, very good. Thank you.
Other questions, comments? I have a general question. It seems like what you're doing is depends strongly on the fact that G is finite. What if G is not?
Yeah, that's a great question. If G is not finite, what goes into this theorem that I mentioned is pretty formal homotopy theory, and not much should break when G is finite. The only thing that really breaks is this understanding of the transfer. But like, so in the classical setting, let's say I did Bézou's theorem and I took like x times y and intersected with y times z. And instead of getting 4 points for my conics, I get a point and a line. You can make sense of that line contributing 3 to your solution by something called residual or excess intercept. And I would imagine if I'm doing something like an S1 action and I get this locus that's not a point anymore, I could still make sense of its contribution to the problem. So you do get like a sum over these sort of local indices. That will still work if your group isn't finite. It's just actually doing any computations with them is not, it's not something that I currently have the machinery to do.
Other questions? Well, if not, let's thank Thomas for a very interesting talk. Thank you very much, Thomas. I'm stopping the recording.